you have any problem, if you don't see the screen, so I'm sharing screen, and I will use the blackboard every now and then, okay? So let me know if there's any problem, if you don't see something, if you don't see clearly what I write on the board, or anything. It would be nice, if you can, to see your faces at least, so we don't get to know each other this year, unfortunately. But at least if I can see your face on the screen is nice, thank you very much. Unless you're still half awake like Giovanni, or you're too embarrassed to show your face because you haven't brushed your teeth. But at least the first 5 minutes just to say hello, okay? But if you can leave your camera on during the whole lecture, is even better, okay? So at least I can see faces, okay? It's much better. Stop it. Since this is not going to be, you know, this year has been difficult, it's still difficult. We don't have much physical and personal interaction. So at least, I don't know how you've been doing it so far, but at least let's try to make it interactive as much as possible. So please ask questions, make comments, tell me whenever I make a mistake. Instead of thinking, oh, he made a mistake, but I know he made a mistake, just tell me, okay? And make comments, tell me you don't understand, tell me you don't agree, whatever, okay? There are no stupid questions, there's only stupid things I can say. Okay, so so you did the first part of the, yeah, for example, you know, I've never seen the face of Severio. Ciao Severio, ciao Andrea. Okay, nice to meet you, kind of meet you. So you did the first part of the course, which I hope was okay, with Miro. Okay, and the first part of the course was more or less, I wouldn't say introductory, but it was descriptive, right? So there was a description of the properties of the ocean, the properties of seawater, temperature, salinity, density, water masses, I guess. There was a description of the movements of the ocean, and Miro told me that he was introducing concepts and then showing the concepts with examples or observations, okay? And but what we're going to try to do in this second part of the course is be a little bit more, I wouldn't say theoretical, but not descriptive, but explaining exactly why the ocean moves and how the ocean moves, okay? So what are the dynamics, the forces, and describing, well, I shouldn't say describing, but giving you an introduction of the theories of the large-scale ocean circulation, okay? So we will see some things that you've seen before in other courses, like GFD especially, and some things that I'm sure you have seen in atmospheric dynamics with Fred, okay? But first, it's good to repeat some things quickly, so that when I introduce something, you have this concept fresh in your head. And then, for example, like the second lecture would be on the Ekman layers and Ekman dynamics. Okay, I know you've seen Ekman layers in GFD. I know you've seen Ekman layers in the atmosphere. And although the theory is the same, the application in the ocean is slightly different. Okay, in the atmosphere you have mostly looked at the bottom Ekman layer for obvious reasons. Okay, in the ocean we will mostly devote our time to the upper or top Ekman layer. Obviously, okay, the ocean is forced from above, and so the top Ekman layer is the one that really matters for the ocean circulation. Unless you're interested in coastal oceanography, in bottom circulation, interaction with the topography, and then you are mostly interested in the bottom Ekman layer. But for the large-scale ocean circulation that we will talk about in this course, we will talk about the top Ekman layer. Okay, and so I will repeat again the theories of the Ekman layer, which I know you've seen before, but I think it's nice to revisit it in the framework of the ocean circulation, okay? And then you will see how that thermodynamics matches the interior ocean circulation. Okay, so I can show you, so I always make the same mistakes. Bad idea to change things the evening before you do something, but I did. Okay, so these are the notes that I will use in the course and that I will give you as the course progresses. Okay, so I will give you chapter by chapter or lecture by lecture. It would be nice if you read the notes. Okay, so if you read the notes and if you give me feedback on the notes, okay, you made a mistake here, there should be a minus, there's a plus, or it's not clear how you go from A to B, you should add something here, this should go before that, okay, so that I can improve the notes. But whatever I say is written in the notes, I think, okay. There's more things in the notes that we will talk about, so obviously don't, so don't look at chapters in the notes that we have not talked about in class. Now I see that because I recompiled this LaTeX file like 2 minutes ago and there's no table of contents. Sorry, just give me a second. So I just wanted to show you what we are going to do. So I will stop sharing the screen a second, recompile, and because it's on a pen. Okay, just give me 1 minute. Stop sharing. Close this. Eject. Terrible idea to do things at the last minute. Okay. No, I don't have to do this. Okay. Coming. Okay. Share screen again. And we're back. Okay, so here at the beginning of the notes you have books that I use to produce this note. Okay, there's a small list of basic books that, if you're interested in knowing more, you could have a look at this. Actually, at the end of these notes, there's also the third part of the course that will be taught by Alessandro Crise. Okay, a few lectures by Alessandro Crise. So I put his notes into my notes. Okay, so you have one single document. So okay, so as I said, there's few more things here that I'm putting together in these notes, things that we've seen in GFD. Do you see my mouse when I move the mouse? Yes? Okay. So in GFD, we've looked at Lagrange derivatives, streamlines and stream function, Gauss and Stokes theorem. Okay, so obviously we're not going to go back to this concept. I'm just putting the same notes here. But we will remind ourselves a little bit about the hydrostatic balance, Rossby number, the hydrostrophic balance, thermal wind, introduce rotation and stratification to then introduce the Rossby radius. Okay. The beta plane, I think we're going to do the beta plane today. Okay, so a good reintroduction of concept that you should know already, but is nice to revisit at least at the beginning. Okay, so there are some chapters in blue that are basically not existent in this notes, okay, that I'm working on it. But otherwise, we're going to go through, so today we're going to start with an introduction, okay, some basic concepts that you know already. And then the second lecture is going to be about friction in the ocean, okay, so we will introduce friction in our momentum equation and derive the Ekman dynamics, okay, so the Ekman layer at the top and at the bottom, and how that relates to the ocean. For example, upwelling, okay, Ekman pumping, and so on and so forth. Not going to do linear waves, and then we're going to go to the first theory of the ocean circulation, which is the wind-driven gyres. Okay, so we will derive all the classical theories of the wind-driven gyres. Then we will have a brief look at thermocline dynamics. You should know what thermocline is. Okay, you should have seen this with Miro, the thermocline and the picklocline. Okay, and we're going to look at the theories of the thermocline, scaling of the main thermocline, what sets the depth of the main thermocline, and so on. Volume transport and heat transport, we're not going to do it, not ready. And but we are going to look at, where is it? Oh yeah, so ocean volume transport, we're going to do this, okay? So buoyancy driven overturning and the wind driven overturning, okay? So I will let you know lecture by lecture what we do in this course and how far we get. Okay, so you will get these notes this afternoon or tomorrow. Okay, so we will start by saying why the ocean circulation is different from the atmospheric circulation. Okay. So as I said already, we're going to see some concepts that we've seen already in GFD in the first part of this course, which is physics, which was the part descriptive physical oceanography. And things that you've seen in atmospheric dynamics as well, but it's good to repeat things and to revisit these theories or these approximations in the framework of the ocean circulation. So the ocean circulation theory, you will see that is based on the same principles as the atmospheric dynamics, okay, with a few changes that we will see. But there are a couple of things that you will notice that make the ocean circulation, although the same equations apply, the same conservation principles apply, there's a few things that make the ocean circulation different from the atmospheric circulation. And I would say not more difficult, but not as generalized as the atmospheric circulation. Okay, the first thing is that the ocean circulation is constrained by the presence of continents. Something obvious, but the presence of continents makes ocean circulation different depending on where you are. Okay, so in the atmosphere, you could cut through at some longitude and make a two-dimensional approximation of the atmospheric circulation. We get the Hadley cells and the Ferrel cells, and it doesn't matter whatever you cut. Okay, you could cut in the middle of the Atlantic, you could cut in the middle of Asia, unless you're interested in the bottom Ekman layer in the atmosphere. The large-scale atmospheric circulation is going to be approximately the same. Okay, this is not true for the ocean. Okay, the ocean circulation in the Atlantic is completely different from the ocean circulation in the Pacific or in the Indian Ocean. And that's mainly because of the presence of continents that shape the circulation differently and make the circulation different because the surface forcing is going to be different. Okay? So the second point is that the ocean, contrary to the atmosphere, is both heated and cooled at the surface. Okay? So there are momentum fluxes at the surface of the ocean and buoyancy fluxes at the surface of the ocean. And that is the main forcing of the ocean circulation. And so you can think already that the Indian Ocean circulation will have different buoyancy fluxes than the Atlantic Ocean circulation, because the Atlantic Ocean goes up to 70 north or something like that, and then becomes the Arctic Ocean, whereas the Indian Ocean is constrained by the presence of the Indian subcontinent. So the buoyancy fluxes are going to be different. Although the main theory that you might start with is the same, then the resulting circulation, because of the surface forcing and the presence of the continents, is going to be very, very different. Okay, and you can see the difference. You've probably seen this with me, but you can see the difference in. You can trace the difference in the ocean interior from the surface. Okay, from the surface fluxes that we will see later, or from the surface properties. For example, you can look at sea surface temperature and sea surface salinity in the ocean. This is from observations. Okay, so if you look at the sea surface temperature, roughly you see warm temperatures in the equatorial regions and cold temperature in the polar regions. You see differences between the Pacific and the Atlantic, but no major differences. Whereas if you look at sea surface salinity, okay, you see a sharp difference between the Atlantic and the Pacific, for example. You see high level of salinity in the Atlantic in the subpolar regions, and very low level of salinity, sea surface salinity, in the subpolar regions in the Atlantic. And this doesn't happen in the Pacific. The fact that you have different sea surface salinity is the result of different buoyancy fluxes at the surface. And that will impact the interior of the ocean and the interior ocean circulation. Now, the reason why the Atlantic is saltier than the Pacific is still controversy, is due to the fact of the many factors. One of them is the width of the Atlantic Ocean and the width of the Pacific Ocean. Okay, the Atlantic Ocean is mainly evaporated basin, whereas the Pacific Ocean is mainly a precipitative basin. And so over the course of millennia, the Atlantic Ocean has become saltier and has started a circulation that maintains this saltier circulation, whereas the Pacific is fresher, less salt. Okay, so a saltier sea surface salinity in the Atlantic will make the surface water denser in the Atlantic, and then convective circulation will develop in the Atlantic, whereas, as we will see in the Pacific, they don't. Okay. So the ocean is forces at the surface. We've seen an example of, kind of an example of surface buoyancy forcing. But mainly the ocean is forced by the surface wind stress. Okay. You know atmospheric, you know the large-scale atmospheric circulation, so you know the theories of the Hadley sail and the surface wind and wind stresses from the atmosphere. And those are the wind stresses that force the ocean. It's actually, as we will see, it's not actually the wind stress that forces the ocean, but it's the wind stress curl. Okay, it's not the wind stress. It's the curl of the wind stress that starts the interior ocean circulation. And we will see the theory for that. So if the main ingredient, as we will see, of the ocean circulation is the wind stress curl and rotation, okay, then you can use the same theory wherever you are, the Atlantic or the Pacific or the Indian Ocean. You use the same theory for the wind-driven circulation, and you're supposed to get the same ocean circulation patterns. But actually, as we will see, the Atlantic will develop a very different circulation than the Pacific, for the reasons that we mentioned and more. Okay. But that is the wind-driven circulation. Then there is a buoyancy-driven circulation that we will talk about towards the end. Okay. But we will start with the wind-driven circulation. So the wind-driven circulation, as we will see, mainly has these three components: the wind stress curl, rotation, and rotation in the through the beta terms that you've seen, okay, the meridional gradient of the Coriolis parameter. So the wind stress curl, beta, and the presence of continents. Those will shape the large-scale wind-driven gyres in the ocean. Okay? And so the same theory applies, so you can take a square box and develop your wind-driven gyre in the ocean. And you can place that square box in the Atlantic or in the Pacific. So we will see that common patterns arise in the Atlantic and in the Pacific. And then depending on the shape of the continent, then the strength of the gyre will be different, the shape of the gyre will be different, the strength of the western boundary current, and we will see what the boundary currents are and how they develop. The shape and the strength of the boundary current will be different because of the shape and some local constraints, but the main theory is the same. Okay? And so perhaps you've seen recently on the news that there was a recent article about the future evolution of the ocean circulation. So somebody took observations from the past, a couple of millennia, I think. Using proxy data, they reconstructed the strength of the Atlantic Ocean circulation, the Thermo-Haaland circulation, the Meridional Libertarian circulation in the Atlantic. Using proxy data, they reconstructed the strength of this circulation. Then they took observational records of the past 50, 60 years. And then they took the projections from models of the strength of the Meridional Overtone circulation in the Atlantic. And so the main conclusion of the study was that there has been a decline in the strength of the Meridional Overtone circulation in the Atlantic, and that during the past century, and that the decline observed was unprecedented in the historical records. So going back to 2,000 years or something through proxy data, there was never such a decline in such a short time in the Atlantic Meridional Overtone circulation. Fantastic study, but how the result got out into the news, the result was that the Gulf Stream, I think they called it the Gulf Stream system, but the Gulf Stream strength declined, and that was unprecedented in the historical records. And so the perception of the public is that the Gulf Stream is slowing down and has been slowing down much more than did so in the past. Okay? So it's nice to put that out in the news, but there is a slight problem in the way it was conveyed to the public, is that it's not the Gulf Stream that declined in strength, okay, that weakened. Because by now you should know that the Gulf Stream is a western boundary current. Okay. And the Gulf Stream, okay, so the Gulf Stream is a boundary current, is a western boundary current, and the Gulf Stream is the western boundary current of the, can you see the board? Yes. We will develop this theory of the wind-driven gyre, and so it doesn't matter if this is the Atlantic, the Pacific, northern or southern hemisphere, okay? We will develop the theory for a square basing. So you develop the theory for the wind-driven gyre, and you find that the circulation goes in the northern hemisphere for the subtropical gyre in this clockwise direction. There is an internal circulation towards the equator, we will see. And this circulation is closed by a western boundary current and this return flow. Okay? We will see the theory for this. Okay? So the western boundary current closes and is part of the wind-driven gyre. And in the Atlantic is called the Gulf Stream. Okay? And how can you develop this theory for the wind-driven gyre? Well, you need rotation, so you need beta. You need the curl of the wind stress, okay? continents. Okay, so boundary. As long as you have these three ingredients, you can develop your theory for the wind-driven gyre, for example, in the Atlantic. And the Gulf Stream is the western boundary current of the wind-driven gyre in the Atlantic. So, in the future and in the past, at least within 1,000 years or so, beta and the rotation rate of the Earth did not change. Okay, boundaries have not changed. I guess if you go a few million years ago, then the continents were different, but not in the past 1,000 years and not in the next 100 years. And the wind stress curl did not change that much. Could have changed a little bit. Okay, there is variation, but not dramatically. So as long as you don't change rotation, you don't change the curl of the wind stress, and you don't change the boundaries, the strength of the western boundary current is going to be the same, because the strength of the wind-driven gyre is going to be the same. Okay? So my point is that saying that the Gulf Stream weakened in the past 60 years or 100 years is the wrong way of putting the news out to the public, because the Gulf Stream as a western boundary current did not change. Is the part of the Gulf Stream system that, as we will see, is the surface circulation of the meridional overturning circulation that weakened. Okay. So we will, I'm saying all this because we will talk first about the wind-driven gyres, and then we will talk about the meridional overturning circulation. Okay. They are connected, of course, but you can develop the theories for the two separately. So there is a Gulf Stream, there is a western boundary current in the Atlantic, and at the same time there is a circulation that is part of the meridional overturning circulation. So it is the meridional overturning circulation that has weakened in the past 50 or so years. Okay, that is true. I'm not questioning the study, which is great. Okay, but is telling the people that the Gulf Stream has weakened, that is partly wrong. Okay, something like watching the movie The Day After Tomorrow. I don't know if you remember that old movie, when they talk about the Gulf Stream that suddenly stops because there was a little ice age in the North Atlantic. It's not the Gulf Stream that stops. The Gulf Stream cannot stop. As long as the wind blows, the Earth rotates, and you have America on one side and Africa or Europe on the other side, the Gulf Stream will not stop. Okay? It's the meridional overturning circulation that could eventually stop. Okay, so that's why we're going to look first at the wind-driven circulation, and then at the meridional overturning circulation, which is both wind-driven and buoyancy-driven. That's why it's important to notice that the Atlantic Ocean, for example, and the Pacific Ocean have different surface fluxes, and so buoyancy fluxes, okay? And the different buoyancy fluxes at the surface in the Atlantic and in the Pacific will generate a different circulation in the Atlantic and in the Pacific. The wind stress is the same, so the wind-driven gyres, the theory for the wind-driven gyres can be used in the Atlantic and in the Pacific. Not much of a difference. They will change because of the shape of the basin, but the theory is the same. But when you go to consider buoyancy fluxes at the surface, the Atlantic and the Pacific are very, very different. And so the circulation that you will develop in the Atlantic is rather different from the one that you develop in the Pacific. So you cannot have one theory for the meridional overturning circulation in every basin, because it's due to the surface buoyancy fluxes, which are different because of the continents, the presence of continents, and the latitudinal constraint in the basins. Okay. Sorry, it took me too long. So this is basically what I said, and a few examples of. Okay, so you've probably seen these maps with Miro in the scripted part of the course. Here you have, this is observations again, Okay, yes, this observation again. And so now we're looking at a zonal mean in the Atlantic Ocean and then later in the Pacific Ocean. Okay, and we're looking at temperature and salinity. So you take the Atlantic Ocean, you make a zonal mean from the South Pole to the North Pole. Actually, no, this is not a zonal mean, this is a 30 west. Okay, sorry, this is a transect. Okay, and you look at the structure of temperature and salinity in the Atlantic Ocean and the Pacific Ocean. So remember what I said, that the buoyancy fluxes at the surface are very different in the Atlantic and the Pacific, and that reflects on the interior structure. And if there's a reflection in the interior structure, there is a reflection in the circulation inside of the ocean. Okay, we will see the geostrophic balance again. So if you have different pressure gradients, density gradients, you will develop different circulations. So in the Atlantic Ocean, you see, of course, common patterns, but what you see is this very cold part of the bottom of the ocean. Okay, this is around zero, below zero. And this is the signature of the Antarctic bottom water. Okay, this is the signature of the Antarctic bottom water that is produced close to the Southern Ocean, close to the Antarctica, okay, through brine rejection. I don't know if you've talked about brine rejection. When you form sea ice crystals, they expel salt. So the water around the sea ice gets saltier because of all this additional salt, gets saltier, gets denser, and it actually becomes the densest water of the ocean. And that's why it falls to the bottom of the ocean. It fills the bottom of the ocean because it's the densest water. And so you form this water mass that is called Antarctic bottom water that fills the ocean. So it's slowly advected at the bottom of the ocean, and that's the Antarctic bottom water. What you see here, this part of the ocean, roughly 2,000, 3,000 meters, is the North Atlantic deep water. I should put numbers there. The North Atlantic deep water is another water mass that is formed, as the name says, in the North Atlantic. So you see it's all water masses. You transform and you generate water masses at the surface through heat, flux exchange, and freshwater exchange with the atmosphere. So the buoyancy fluxes that you receive at the surface will generate the water masses that fill your basin. So North Atlantic deep water that is formed in the North Atlantic regions. There are a couple of main sites for this deep water formation. And there you form North Atlantic deep water because the surface ocean is in contact with a very cold atmosphere. And you also have brine rejection because of the formation of sea ice, less and less sea ice in the North Atlantic. So you form water that is relatively denser, that goes down to a certain depth, 2,000, 3,000 meters, and then starts to propagate because of pressure gradients, starts to propagate southward, so crosses the equator. Okay, and as you will see, I don't know if you see the same colors, but this blue region, which is North Atlantic deep water, is above this darker region, which is the Antarctic bottom water. And that's because the North Atlantic deep water, as the name says, is deep, is not bottom. So it's not as dense as the Antarctic bottom water. So the surface properties that that water mass acquires, in terms of density, for example, will then be advected into the interior of the ocean. And then it will find its buoyancy and circulate and fill the ocean interior. Okay? So the North Atlantic deep water will flow above the Antarctic bottom water. So you have Antarctic bottom water formed at the surface close to Antarctica, and then you have North Atlantic deep water formed at the surface of North Atlantic, flowing above the Antarctic bottom water. Okay? And then you see, I don't know if you can see, but then you see this North Atlantic deep water that is rising up to the surface. If you don't see it, I'm telling you. Is rising up to the surface, and is rising up to the surface for two main reasons. One is mixing, but the stronger reason that is upwelling to the surface is because of wind-driven upwelling in the Southern Ocean. And that's why we will talk about Ekman dynamics and Ekman upwelling again in this class, because it's very important for the ocean circulation. So this North Atlantic water would be upwell to the surface, exchange fluxes with the atmosphere, and that water mass will be transformed into different water masses again. So this, and with different densities, and so it will flow at different depths. So the buoyancy flux exchange at the surface will determine somehow this water mass structure inside of the ocean and make the ocean circulate. Okay? So this is deep and bottom circulation that has little to do with the wind-driven circulation that we will talk about first. Okay? But this is what is happening below the wind-driven influence in the ocean. If you look at the salinity structure in the Atlantic, it's even more clear than in the Pacific, than in the temperature structure, what I just said. Okay? This is the Antarctic bottom water signature. You see this very salty water mass flowing in the bottom of the ocean. Then here you see the signature of the North Atlantic deep water being advected to a certain depth, 2,000, 3,000 meters, and then slowly propagating southward. And then this pink, low salinity tongue of water that you see that then propagates equatorward is called Antarctic intermediate water. I don't know if you've seen all these names of water masses with MEO, but anyway, you don't have to remember this. It's just to give you an idea of the interior circulation. And that Antarctic intermediate water, this, is partly generated by the upwelling of North Atlantic deep water. So you have North Atlantic deep water upwelling to the surface. It's transformed by buoyancy fluxes at the surface. Part of this North Atlantic deep water becomes Antarctic bottom water because it becomes cold and it becomes very salty. And part of this North Atlantic deep water that upwells slightly equatorwards becomes less salty because it's far away from the sea ice region, but cold enough as to sink as Antarctic intermediate water. Okay? So you have something like this going on. If this is depth, okay, and this is latitude, minus 80 to 80, you have North Atlantic deep water upwelling through Ekman upwelling in the Southern Ocean. Part of this water mass is becoming Antarctic intermediate water, and part of this water is becoming Antarctic bottom water, okay, roughly speaking. And this is all due to buoyancy fluxes exchange at the surface that transforms these water masses. So the buoyancy fluxes at the surface will determine the water mass structure in the ocean and the deep and bottom circulation in the ocean. So that's why buoyancy fluxes at the surface, that's why it's so important to set up the interior circulation in the ocean. Okay? If you look at the Pacific Ocean, you see that the structure is completely different. It's again a section along the Pacific Ocean, north-south, and you get a totally different picture. Especially if you look at the northern hemisphere, you don't find deep water production, okay, this tongue. You don't find deep water production because there's no deep water production in the Pacific because the buoyancy fluxes are different. The Pacific doesn't reach latitude as far north as the Atlantic. And so the buoyancy fluxes that the North Pacific will receive are different from the buoyancy fluxes received by the Atlantic Ocean. So there's no deep water production. And so there is no deep circulation in the Pacific. That's why the meridional overturning circulation, every time that somebody talks about the meridional overturning circulation, is mainly focusing in the Atlantic Ocean, because the Atlantic Ocean is where you have this major conveyor belt meridional return circulation. Okay? The Pacific has a circulation, but it doesn't have a deep circulation. And if you look at the salinity structure again, you see intermediate water formed close to Antarctica, but you see a smaller signature in terms of Antarctic bottom water, because most of the Antarctic bottom water is produced in the Atlantic. Okay? So this is again an example that in the atmosphere, I'm not trying to say that atmospheric dynamics is simpler than ocean dynamics, but in the atmosphere you can cut through the atmosphere at a certain longitudes and you can develop your 2D theory for the atmospheric circulation. In the atmosphere, in the ocean, you cannot do the same. Okay? If you cut in the Atlantic or if you cut in the Pacific, you get a totally different structure and you get a totally different circulation. And that's because of different forcing at the surface and the shape of the continents that will constrain the ocean circulation both at the surface but also in the interior. Okay, so if we go back to the surface circulation, so the wind-driven circulation, we said that you mainly need three ingredients: rotation through beta, okay, which is just dF by dy, okay, the meridional gradient of Coriolis. Then you need the wind stress, but not just the wind stress. What you need is the curl of the wind stress. Okay, we see that what sets up the circulation, the wind-driven circulation in the ocean, is just the wind stress. If you have wind stress, you develop Ekman dynamics. Okay, you develop the Ekman spiral, you develop an Ekman transport. But in order to set up the gyre, the large-scale ocean gyres, you need the curl of the wind stress. Okay. And then you need continents. Okay. So meridional boundaries, basically, in your equations, you will need you need boundary conditions. Okay, so continents are just my boundary conditions. Once you have these three ingredients, then you can develop your wind-driven gyre theories. Okay, and so continents will change a little bit, but you have the same boundary conditions east and west. The wind stress curl, if you know atmospheric dynamics, you know that the large-scale climatological wind stress, for example, in the Atlantic and the Pacific, is roughly the same. Okay, you have westerlies and easterlies. You have the trade winds, and you have the westerlies. So there might be slightly stronger or weaker. There might be slightly displaced to the north or to the equator, but you get the same sign of the wind stress curl. Okay, roughly at the same latitude. So you will develop, and beta, of course, is the same in the Atlantic and in the Pacific. So you will develop roughly the same wind-driven ocean gyre in the Atlantic and the Pacific. And if you switch sign and you go to the southern hemisphere, you get the same wind-driven gyre in the southern hemisphere, but with a different sign. Okay, and so that's why, if you look at this schematic, okay, of course, it's much more complicated than this. The regional details and the coastal details, especially at the equator, close to the continents. But a good approximation of the main surface currents in the ocean is given by these schematics. Okay, so if you look at the red arrows, in the Atlantic and in the Pacific, you have those clockwise circulations. Okay, both in the Atlantic and the Pacific, because they are set up by these three main ingredients. You have a thicker arrow on the western side, because that's the western boundary current. And the western boundary current, as we will see, is stronger, is faster than the eastern boundary current because of simple conservation principles. So both in the Atlantic and in the Pacific, you will develop a clockwise subtropical wind-driven gyre. But the shape is different because the shape of the continents is different. Okay, so in the Pacific is wider, in the Atlantic is slightly more narrower. But the physical mechanism of the wind-driven gyre is the same. So you have a western boundary current in the Atlantic, which is the Gulf Stream, and you have a western boundary current in the Pacific, which is the Kuroshio. If you move north, so you go to subpolar regions, and you have those blue arrows, okay? There is slightly more difficult from this schematic to realize that they are also gyres, okay? Going the opposite directions, anti-clockwise. So you have the subtropical gyre in the North Atlantic and the subtropical gyre in the North Pacific. Same three ingredients, but in this case, the wind stress curl has changed sign in the subpolar gyre, both in the Atlantic and the Pacific. And so if you flip sign in the wind stress curl, then you get a circulation that is going anti-clockwise. There, the continents shape and constrain the gyre much more than did in the subtropical region, and so it's slightly more difficult to realize a nice gyre going on, but there is a subpolar gyre in the Atlantic and in the Pacific as well, with the same three main ingredients. If you look at the southern hemisphere, you got exactly the same thing. What changes sign now is Coriolis, okay? And you have a subtropical gyre in the South Atlantic and South Pacific. You actually get a subtropical gyre in the Indian Ocean. You don't have one in the northern hemisphere because there's a continent, and so you cannot develop a subtropical gyre in the northern hemisphere of the Indian Ocean. But you have one in the southern hemisphere. So in the southern hemisphere, you have these three subtropical gyres, Atlantic, Pacific, and Indian Ocean, that are set up by these three main ingredients. Okay? And so if you want to develop a theory for the subtropical gyre in the North Atlantic or South Pacific, you have the same set of equations, you have the same dynamics going on. What changes is the sign of the wind stress curl or the sign of F, and the shape of the continents. Okay. Then you have something completely different, which is south of Australia and South America and Africa, which is the Antarctic circumpolar current. The Antarctic circumpolar current, as you see, doesn't have boundaries east and west. Okay, there are no continents that are blocking the current. So, as we will see mathematically, you don't have the boundary conditions there. And so a totally different circulation is developed there. You don't have a subtropical gyre in the South Atlantic and South Pacific because you don't have the same boundary condition. And so what you get is this Antarctic circumpolar current that flows around Antarctica without being stopped by any continent. And a totally different dynamics is set up in the Antarctic circumpolar current. And if we have time to have a look at the dynamics of the Antarctic circumpolar current, you will see that the theory that explains the main features of the Antarctic circumpolar current is just the theory of the atmospheric dynamics. Okay, so it's totally borrowed from atmospheric dynamics because just like in the atmosphere, you don't have any continents blocking the flow, and so the residual the residual mean flow theory of the atmosphere is just used to explain the Antarctic circumpolar current. So it's totally borrowed from atmospheric dynamics. Okay, so these, as for the buoyancy fluxes, from the buoyancy fluxes, and so from the surface buoyancy fluxes, heat flux and freshwater flux, if you ever look at those surface fluxes that I should have here, but I don't, you can infer or you can imagine the interior circulation in the ocean. If you produce dense water, if you produce bottom water, where you do and where you don't. Okay. The same thing is for the wind stress. Because we said that the wind-driven gyres are mainly driven by wind stress curl, then if you have a look at the wind stress curl, timing of the wind stress curl, you know which direction the wind-driven gyres are going to go and where you can develop a wind-driven gyre in the ocean and where you don't. Okay, So here you see the zonal wind stress. This is the meridional component of the wind stress. This is observations or reanalysis. If you look at the wind stress curve, which is what is driving the wind-driven gyres, okay, you know that here you will generate a subtropical gyre clockwise. Here you will generate an anti-clockwise wind-driven gyre, and the same in the Pacific and the southern hemisphere. Okay. So if you have a look at the wind stress curve, you know where the direction of the wind-driven gyre is going to go. Roughly. So map of the wind stress. Okay, this is another schematic of water masses in the well, it's mainly in the Atlantic Ocean. Yes. Okay. So we will talk about the wind-driven gyre circulation first, which is here at the depth of the interior thermocline. Okay, so the reaching the bottom of the depth influence of the wind stress, and so we will develop a theory for the wind stress for the wind-driven gyres here or in the southern hemisphere, and then we will look at the interior circulation, so the meridional Overtone circulation, which is mainly achieved by this cell of the North Atlantic deepwater production in the Atlantic, then circulating all the way to the south, then upwelling through Ekman upwelling, and part of this will generate Antarctic intermediate water that will close this cell, this clockwise cell, which is at deep levels, so 2,000, 3,000 meters. And then there is a bottom cell below this that is formed by Antarctic bottom water that is generated in the southern hemisphere, close to Antarctica. This Antarctic water is the denser water, fills the bottom of the ocean, then is mainly mixed with warmer waters, and recirculates below the North Atlantic deep water, and upwells again at the latitudes of the Southern Ocean where you have strong Ekman upwelling. Okay? And these two cells, this meridional Overtone circulation, is driven by, as I said before, the meridional Overtone circulation is driven by buoyancy fluxes, okay, because you have buoyancy fluxes here and here that produce North Atlantic deep water and Antarctic bottom water. And so that's why originally this circulation was called thermohaline circulation, because the thermohaline circulation, as the name says, is due to changes in temperature and salinity at the surface through buoyancy fluxes that change temperature and salinity structure, therefore density, and sets up this deep and bottom circulation of the meridional Overtone circulation. But then people realize that once you generate this North Atlantic deep water or Antarctic bottom water, in order to close the loop, in order to close the cell, you need to bring this cold water back to the surface. And so the only way to bring this dense cold water back to the surface in the original theory was mixing. Okay? And so the theory was that you needed mixing to mix this cold water to bring it back to the surface and then close the cell. But then actually measurements came of mixing in the ocean, and the mixing estimates in the interior of the ocean were something like 2 or 3 order of magnitude smaller than the mixing required to mix the volume, all the volume of North Atlantic deep water, to mix it in order to upwell it back to the surface. So in the original theory, if you just consider mixing to close the cell, if you're not following, make questions, comments, stop me, okay? I don't hear anyone. So if you have North Atlantic deep water production through buoyancy fluxes at the surface, okay, then in order to close the cell and bring this North Atlantic deep water back to the surface, originally, if you just consider buoyancy fluxes, the only mechanism that you could imagine was mixing, okay, through some mixing coefficient kappa. And so if you make the calculations of how much volume of North Atlantic deep water you produce, how much mixing do you require to bring all this volume of North Atlantic deep water back to the surface to mix it in order to make it warmer, lighter, and bring it back to the surface? Well, the mixing required, theoretically, was 2 or 3 order of magnitudes larger than the estimates of mixing observed. Okay? And so they realized that mixing could not be the only mechanism by which you couldn't bring North Atlantic deep water back to the surface, because the mixing observed is much, much smaller than the one that you required. So what is the other mechanism that could bring all this North Atlantic deep water back to the surface? So if this is the equator, this is north and this is south. The other way, so mixing would be not localized, but throughout the Atlantic Ocean you have mixing. Okay? And all this mixing is much smaller than the one required theoretically to bring all this North Atlantic deep water back to the surface. So the other way you can bring North Atlantic deep water back to the surface is through Ekman pumping. So upwelling, Ekman wind-driven upwelling. And so the wind-driven upwelling happens in the Southern Ocean, in this region. This gray band is the Drake Passage band. The Drake Passage is this region, okay, between the Antarctic Peninsula and South America. This is called the Drake Passage. And so most of the Ekman upwelling happens in the Southern Ocean, because as we will see, you can generate Ekman upwelling there, okay? And it's a very strong Ekman pumping. And so in those regions, you can bring all this North Atlantic, most of this North Atlantic deep water back to the surface. That then closes the loop, or some of this actually generates the Antarctic bottom water, okay? So the amount of North Atlantic deep water that you can mix up to the surface throughout the Atlantic, as this North Atlantic deep water flows southward, is only a small fraction compared to the amount of North Atlantic deep water that you can bring up to the surface through wind upwelling. Okay, so the thermohaline circulation is not called the thermohaline circulation anymore. It's called meridional Libertarian circulation. So there's no mention of the driving forces of the circulation, because it's not just buoyancy driven at the surface, so temperature and salinity, but it's also and mostly driven by wind-driven upwelling in the Southern Ocean. Okay. Many people did, I also did this experiment. If you in a numerical model, if you remove wind-driven upwelling in the Southern Ocean, the only way you can bring North Atlantic deep water back to the surface and close the circulation is through mixing. And if you use observational estimates of mixing or realistic mixing, this North Atlantic deep water cell or the meridional Overtone circulation weakens a lot or almost disappears. Okay, so diapirconal mixing in the ocean is not sufficient to sustain the meridional Overtone circulation. You need Ekman pumping in the Southern Ocean to sustain the meridional Overtone circulation as we know it today and in the recent past. Okay, so that's why people don't talk about thermohaline circulation anymore, because it's not just buoyancy fluxes. Actually, you need wind stress. Okay, so this is going to be the meridional Overtone circulation, MOC. And most of the meridional Overtone circulation happens in the Atlantic, because it's where you form North Atlantic deep water. Okay, so you need wind-driven upwelling in the Southern Ocean. So the wind-driven gyres are only driven by wind stress, whereas the vertical meridional overturning circulation in the ocean, that, as we will see, involves all the different ocean basins, is driven by both buoyancy fluxes and wind stress at the surface. Okay, so you need both. So just separating the circulation into a wind-driven circulation, the gyres, and the meridional overturning circulation is a bad approximation, because the meridional overturning circulation needs the wind stress and the wind stress curl to be sustained. Okay. And going back to the news of the Gulf Stream is declining, it's a bad approximation. It's a bad statement, because it's not the wind, it's not the Gulf Stream that is weakening. It's the meridional overturning circulation that is weakening because of changes in the buoyancy fluxes in the North Atlantic regions. And part of this upper part of the meridional overturning circulation flows within the Gulf Stream system, but it's not the western boundary current Gulf Stream. I hope that was clear. Okay, and this is a schematic of the global meridional overturning circulation. Okay, and so if you focus on the North Atlantic, if you focus on the Atlantic, if you focus on the Atlantic, okay, start from the subpolar regions in the Atlantic, you see two yellow dots, L and N. Okay, L is the Labrador Sea and N is the Nordic Seas. Those are the two regions, the two main formation regions for North Atlantic deep water. Those are the regions where most of the North Atlantic deep water is formed, because the surface of the ocean becomes cold enough, because it's in contact with a cold atmosphere, and salty enough because of sea ice formation, brine rejection. The surface of the ocean becomes saltier, and so the properties of the seawater at the surface becomes dense enough as to sink down to 2,000 meters or so. Okay, so it's mainly localized in these two dots, these two regions, Labrador Sea and Nordic Sea. That's where you can form convection. It's called open ocean convection, okay, because it's not coastal convection. There's a difference. In the ocean, we talk about open ocean convection and convection along the shelf. So in these two regions where you form open ocean convection, you have these large chimneys of convection going down to roughly 2,000 meters. Okay, and then you form that blue arrows. Okay, and that blue arrows starts flowing at roughly 2,000 meters. It goes to the west of the basin. We will see the theory for this. Okay, we will see why it goes to the west and it doesn't go to the east. There's a simple theoretical reason. It goes to the west and it crosses the equator, and if you follow the blue arrows, goes all the way down to the Drake Passage. Okay, as it goes down, as it's going down, the blue arrows, you see some red dots. Okay, red dots with a circle, with a red circle around it. That's mixing driven upwelling. Okay, this upwelling that I was talking about. Okay, so as it's flowing southward, there is upwelling, mixing driven upwelling. Okay, this kappa, this diapicnal mixing, but it's not very large. It's not large enough. Okay, it's not large enough as to bring all the North Atlantic deep water back to the surface, and so a lot of this North Atlantic deep water keeps flowing southward until it reaches the Southern Ocean. Okay, when it reaches the Southern Ocean, you find a strong Ekman upwelling. And so all this North Atlantic deep water is upwelled to the surface, and it becomes a different water mass. Okay. If you focus just on the Atlantic, then it becomes these red arrows and flows again equatorwards and closes the loop. Okay? And so we have this simple schematic of the Atlantic meridional overtone circulation. You see that the surface red flow goes again to the west, okay? And it goes again to the west as it flows northward and becomes part of the Gulf Stream system. But it's not the western boundary current that we call Gulf Stream, okay? And so it's not the Gulf Stream that is weakening. It's the surface flow of the Atlantic meridional overtone circulation that is weakening, because all this overtone circulation is weakening. Okay? You could stop the meridional overtone circulation and still have a wind-driven gyre with a western boundary current and a Gulf Stream. Okay? So it's two things, one on top of the other, let's say, but dynamically independent. As the water is upwelled in the Southern Ocean, you could just focus on the Atlantic and make this simplified schematic of the meridional overtone circulation. Or you could actually realize that you said that, well, this black dot is the wind-driven upwelling that happens throughout the Southern Ocean that upwells all this North Atlantic deep water. But once the water upwells to the surface, then it could flow back into the Atlantic or follow the Antarctic circumpolar current that we said is a very strong current that flows along Antarctica, and then circle around Antarctica, and then some of this water can go into the Indian Ocean and some other part of this water can go into the Pacific Ocean. Okay? The only way you can upwell waters in the Indian Ocean and the Pacific Ocean is through mixing. Okay? So these red dots. So how you close the loop, how you upwell water in the Indian Ocean that becomes surface water, and how you upwell water in the Pacific Ocean that becomes surface water, is through diapicamol mixing. You don't have upwelling there, and you don't have deep water formation regions. You don't have yellow dots. Okay? The only yellow dots that you have are in the North Atlantic, Labrador Sea and Nordic Sea, and around Antarctica, where you form Antarctic bottom water. Okay? So roughly those two yellow dots, Weddell Sea and the Ross Sea. Again, two regions where you form deep ocean convection and you generate this very dense water. Okay? So the circulation that, again, this is a schematic, very simplified schematic of the main features of the meridional overtone circulation, but the point is that you form deep and bottom waters in roughly four localized regions, North Atlantic and close to Antarctica, where you form North Atlantic deep water and Antarctic bottom water. That mixing is not enough to upwell all this North Atlantic deep water. You need Ekman wind-driven upwelling in the Southern Ocean to close the circulation. And that you don't form deep waters in the Pacific and in the Indian Ocean. So, because you don't have the same buoyancy fluxes. You see the Pacific doesn't reach as far north as the North Atlantic. And so the buoyancy fluxes that it receives are totally different, and much more so the Indian Ocean. So the circulation in the Atlantic is completely different from the circulation in the Pacific and in the Indian Ocean, because you can form deep waters. This has many consequences. Okay. First, you cannot have a general simplified description of the meridional overtone circulation that is valid for each and every basin. Okay. What happens in the Pacific is totally different from what happens in the Atlantic Ocean. And then this also means that because deep water formation or bottom water formation is very, very localized, Labrador Sea, Nordic Sea, Ross Sea and Weddell Sea in the Antarctic continent, this also means that, so this global meridional overtone circulation has this 4 valves, let's say, okay? These valves where the ocean breathes, is in contact with the atmosphere, loses heat to the atmosphere, the ocean becomes dense and sinks to a certain depth, okay? So they are called valves of the ocean, where the ocean breathes. And this means that the Atlantic Ocean is very important for the global meridional Overtone circulation. This also means that the meridional Overtone circulation is very sensitive, because if you mess around with one or more than one of these 4 valves, you influence not only the Atlantic meridional Overtone circulation, but the meridional Overtone circulation in the Pacific and in the Indian Ocean after a few decades or centuries. Okay? So the meridional Overtone circulation is very sensitive to localized changes in buoyancy fluxes or circulation. For example, as sea ice concentration and volume is decreasing in the North Atlantic and in the Arctic regions, and we have good observations for that, unfortunately, there is less sea ice formation in the North Atlantic region, Labrador Sea and Nordic Sea, so there is less brine rejection, and so the water in that region, the surface water, is becoming less salty, less dense, and so more buoyant, and so the production of North Atlantic deep water is somehow weakening. And also, you not only produce less sea ice, so there is less brine rejection, but you're also melting the sea ice that you have, the permanent sea ice. And if you're melting sea ice, you are releasing a large amount of fresh water at the surface. So not only you're making the water less salty through less brine rejection, but you're also making the surface North Atlantic fresher because you're melting sea ice. So it's kind of putting a lid in these 2 valves, yellow valves, the Labrador Sea and Nordic Sea. And so the observations and numerical models are showing us that the North Atlantic deep water, and so the Atlantic meridional Overtone circulation, since it is very sensitive to those 2 localized regions, has been affected in the past 50, 70, or 100 years by the changes in surface properties in the North Atlantic. And so what is changing is the volume of North Atlantic deep water that has been formed at the surface. And if that volume is diminishing, the strength of this circulation is also changing. And if you change the strength of the Atlantic meridional Overtone circulation, then you change the strength of the global meridional Overtone circulation in the Pacific and in the Indian Ocean. Okay? It takes a few decades or centuries for that information to be transmitted to the Pacific and in the Indian Ocean, but eventually it would reach the Pacific and in the Indian Ocean. So that's another reason why the ocean circulation is different from the atmospheric circulation, is because this is just one of the examples that show you how the global ocean circulation, could be meridional Overtone circulation or something else, is dependent on localized features. Could be, in this case, open ocean convection in the Labrador Sea that affects, after a few decades or centuries, the global structure of the deep ocean. Or it could be the opening or closing of the Drake Passage. If you open or close the Drake Passage, that not only will affect the Atlantic meridional Overtone circulation, but it will affect the global meridional Overtone circulation. And the same thing for the, this is a big problem in global ocean models, is the Ross Sea and the Weddell Sea. And so basically the production of Antarctic bottom water. Okay? So producing Antarctic bottom water in ocean models through open ocean convection is relatively easy. You can generate open ocean convection in the Ross Sea and Weddell Sea, very deep mixed layers reaching down to 2,000, 3,000 meters, huge chimneys of Antarctic bottom water production, and this Antarctic bottom water is formed. But actually the observations say that Antarctic bottom water, in reality, is not mainly produced by open ocean convection, but is mainly produced by convection along the shelf of Antarctica, where you have sea ice formation and exchanges with the atmosphere that makes the water very cold. Okay? Most of the Antarctic bottom water in reality is formed along the shelf of Antarctica. Okay? Most of the sea ice formation happens there. And this is difficult to represent in ocean models because in order to do that you would need a very, very high resolution ocean model that correctly represents or accurately represents the continental shelf of Antarctica and all the sub-mesoscale mixing that happens along the shelf. Okay. That is in climate ocean models, so ocean models that are used for climate studies, very long integrations, is not possible. Okay, you would need a resolution that is too much for ocean models of these generations. So in global ocean models that are used for climate, the resolution is too coarse to represent convection along the shelf. And all of the Antarctic bottom water is formed in open ocean convection. Okay? And that is not enough. And so Antarctic bottom water produced in ocean models is generally too weak compared to the observations. And so I was saying this because this is another example of the fact that in order to get a proper, you run your ocean model for 5,000 years, gets to equilibrium. That's another difference with the atmosphere. An atmospheric model, you run it for 2-3 years and it's in equilibrium. The ocean has a diffusive time scale. It takes 10,000 years to be in equilibrium, the bottom of the ocean. And so you run for 10,000 years your ocean model, and then you realize that you're not producing any Antarctic bottom water. So your vertical structure, temperature and salinity is not correct. And you know that Atlantic deep water, because it doesn't have an Antarctic bottom water, can actually reach deeper layers of the ocean, which is slightly unrealistic. And eventually the strength of your circulation is not correct. And so you might not be happy with the simulation of your numerical model, and the problem is not any large-scale feature or any fundamental problem in your equations that you have put in your model. The problem lies in the resolution of the continental shelf of Antarctica. Okay, so a small detail, in this case topography, can affect the global ocean circulation after a few thousand years. Okay, I lost my any question? Come on. No question. Okay, and this is a model. Okay, this is a model solution of the global meridional Libertarian circulation. I should stop in 10 minutes. This is the stream function of one of the models that I use. Okay, and you see what you see here is the global meridional Libertarian circulation. So the stream function that we will see later, the stream function of the zonally integrated and vertically integrated meridional velocity. Okay? So you compute your stream function, and then, as you know, the strength of the circulation is given by the difference between the two stream functions, two streamlines. We've seen this in GFD. Okay. And so the red part of this stream function gives you a clockwise circulation, positive in this for convention, and blue is negative circulation or anti-clockwise. Okay. What you see in this plot is exactly what I was trying to show you here. Okay, in red, in the north, this is global, but if you do a zonal integration within the Atlantic, you basically get the same structure. The magnitude weakens because you're not integrating the Pacific and the Indian Ocean circulation. But this clockwise cell exists in the global meridional Overtone circulation because of the Atlantic. Okay, in the Pacific it doesn't, because that's North Atlantic deep water. This is North Atlantic deep water being formed in the North Atlantic with a strength of roughly 26 Sverdrup in this model, and then flowing all the way to the Southern Ocean. There is some closing of the circulation, and that would be through mixing. Okay, but most of the North Atlantic deep water flows almost isopycnically to the Southern Ocean, where it is upwelled to the surface through wind-driven upwelling, and then it closes the circulation. Okay, so this circulation, although this integration is global, if you have a look at the Atlantic meridional Overtone circulation, has the same structure but weaker in magnitude. But this wouldn't be weaker because it's all transport that happens in the Atlantic, but the rest will be weaker. Then what you have below the North Atlantic deep water, which we call the upper cell, okay, so this would be the upper cell. What you have below in blue is the lower cell. And the lower cell is made of Antarctic bottom water being produced in the southern hemisphere, then filling the bottom of the ocean, and then being upwelled again in the southern ocean. Okay. The Antarctic bottom water in this model is roughly 4 Sverdrup or 6 Sverdrup, something like that. In reality, is larger than that. So this model, as many or most climate models, produces very small amounts of Antarctic bottom water. And that because it's too coarse to represent shelf processes. And because it's not representing shelf processes, is producing less Antarctic bottom water. And so the global meridional Overtone circulation is slightly different than reality because of not being able to reproduce shelf waters. Okay, so there was a lot of blah blah blah, but I hope I gave you a good introduction of basically how we will structure the description of the large-scale ocean circulation. Okay? So we will talk about the theories of the wind-driven gyres. We will spend a lot of time in that. How you form wind-driven gyres, how you form a western boundary current, why the western boundary current is in the west and not in the east. And then we will talk about the meridional Overtone circulation, which is both buoyancy driven and wind driven, as we know. Okay? And something I didn't say is that because of this, then the Atlantic Ocean not only has a strong impact on the global circulation, but also on the climate implication of the ocean circulation. Okay? Because as the ocean breathes at the surface in the Labrador Sea and Nordic Sea, it takes up heat and CO2 from the atmosphere and brings it down to deeper layers. So it buries, for example, traces like CO2 to deep layers. And the same is doing the Southern Ocean. Okay. So the North Atlantic and the Southern Oceans are the main regions of CO2 uptake by the ocean. So and that's why the Atlantic Ocean is so important for climate. Also because as the circulation that you see there, most of the heat transport in the ocean happens in the Atlantic. You have the heat transport due to the wind-driven gyres, which is roughly the same in the Atlantic and in the Pacific. But the heat transport associated with the meridional return circulation is mostly achieved by the Atlantic Ocean, that transports warm water all the way up to the subpolar Atlantic. Okay? So most of the heat transport is done by the Atlantic Ocean. So most of the excess heat that we are putting into the atmosphere and CO2, the part that is absorbed by the ocean, most of the absorption happens in the North Atlantic and the Southern Ocean because of this global meridional return circulation structure that makes the North Atlantic and the Southern Ocean so important. Okay. I think that roughly 40% of the CO2 that we have emitted into the atmosphere has been absorbed by the ocean. And of that 40%, something like 70% or 60% has been absorbed by the Southern Ocean, okay, and the rest by the North Atlantic. So that's why the Southern Ocean, the Atlantic Ocean, and in general the ocean is so important, because, well, you can imagine that if the ocean circulation was not there, and if the ocean would not suck as a sponge excess heat and CO2, I think that the atmosphere would have been by now 5 or 6 degrees warmer than it is, because 40%, 35 to 40% excess CO2 that we have emitted has been absorbed by the ocean. The land absorption of CO2 is very small, the atmosphere is very limited, so 40% of excess CO2 has been absorbed by the ocean. And the ocean has buried that CO2 into its deep and bottom layers in the North Atlantic and Southern Ocean. And so people have done experiments that if you remove CO2 absorption by the ocean circulation, there would have been much more CO2 in the atmosphere, and the atmosphere would have heated up by 5 or 6 degrees warmer. Okay, so the meridional circulation is important not just to redistribute heat and mass or volume in the ocean, but also because of the climatic influence of the ocean in terms of sucking excess heat and CO2. Unfortunately, that CO2 that the ocean circulation is burying into its deeper layers, and is a good news for us that we live in the atmosphere, eventually that excess of CO2 will be upwelled if it's not remineralized. Only part of it is mineralized. So that excess of CO2 will be, those two regions where I said that the ocean breathes. So the ocean breathes, inhale CO2 in some places, so it takes CO2 in some places, but exhales CO2 in some other places. So in the Southern Ocean, this North Atlantic deep water that has absorbed anthropogenic CO2 will get in contact again with the atmosphere in the Southern Ocean, and it will expel the anthropogenic CO2. So in the Southern Ocean, there is both absorption of anthropogenic CO2, but also breathing out anthropogenic CO2. Okay. So eventually, that excess CO2 that we put in the atmosphere and that the ocean is helping us by absorbing it in and storing it in deeper layers, then eventually most of that anthropogenic CO2 is breathed out at the surface in some other places like the Southern Ocean. So it's definitely not going to help us for long. And actually it's not clear yet if the net CO2 flux in the Southern Ocean, if it's positive or negative, because of the breathing out of anthropogenic CO2 and the breathing in that happens in the Southern Ocean. So there are places, depends on the season and the places, but the net CO2 flux is not yet clear. Okay, I think I'll stop here, and the next time we'll talk about we will revisit again, geostrophic balance, Rossby radius, the beta plane, and then we will start with the dynamics. Do you have any questions, please, or comments?
Nothing at all.
Okay, I'll stop sharing my screen. Was it clear? Okay, good. I'll see you on Wednesday. And I'll send you the slides lecture by lecture, okay? The notes, lecture by lecture. Have a good day.
Thank you.
Bye.
Thank you. Thank you. Bye.